In the last segment, we talked about running addition reactions of alkenes using water with an acid catalyst to give a so-called hydration product, where the product corresponds to adding H and OH across the carbon-carbon double bond, giving an alcohol as the final major product. A possible pitfall of the acid-catalyzed hydrations that we talked about before is that they are prone to carbocation rearrangements. So you might not always get a product that corresponds to just adding OH and H across the carbon-carbon double bond following Markovnikov's rule. Instead, there might be that extra step of carbocation rearrangement in there. So what if you want to do a reaction to give hydration, an alcohol product, that doesn't involve a carbocation rearrangement? The solution to that is doing a technique called oxymercuration reduction, and that's going to be the topic of this unit. So what I'm talking about here when we say that we want to do a reaction that does not involve carbocation rearrangement is we're trying to ask the question of how we could do the reaction shown here, where we start with an alkene, we add H to the terminal carbon on the far right there, right here, and OH to this one. So we are following Mark's rule because we're adding H to the carbon that has more hydrogens. But we want to do this without having a carbocation rearrangement. So the trouble we would run into if we used the acid and water technique, what we would see is that we would obtain this product. So we would see if we did the hydration using acid catalyst and water, that we would first, as shown here, bring the pi electrons over to do protonation. That would, of course, follow Mark's rule here at step 1 to give a secondary carbocation. Then that secondary carbocation would undergo a 1,2 rearrangement in step 2 of the mechanism to convert that secondary carbocation into a tertiary carbocation, which you've seen before. Then what would happen in steps 3 through 4, which I'm not going to show entirely since we've seen this before, is that the water would come in, act as a nucleophile to attack that tertiary carbocation, and then that would be deprotonated to give a hydroxy group in your final product. So the problem with using water and acid catalyst is that if your goal is to make regioselectively this constitutional isomer, rather than this one, shown down below, you're not going to be able to do that using water and the acid catalyst, because instead you will have this rearrangement take place. So what if we want to do a reaction that does not have carbocation rearrangement? So what if our goal is to make this molecule shown here at the top? How in the world do we go about doing that in a way that will have a high yield to give this as the major product rather than as a very, very minor inconsequential product? Oxymercuration reduction is going to be our solution. So let's go through how to do that, what reagents we'll use, and the mechanism for key parts of this reaction. So let's take this same example problem, and now we're going to fill it in with the oxymercuration reduction to show how we can make the desired product out of that reactant without a carbocation rearrangement taking place. So let's go ahead and get that going right now. So make sure I get this spelled right, oxymercuration reduction. So with regard to oxymercuration reduction, just a couple of facts as we get started. Number 1, as I alluded to in the last few moments, there will be no carbon skeleton rearrangement occur during oxymercuration reduction. In other words, we're going to directly add H and OH across the carbon-carbon double bond without any rearrangements during the process. So no movements of methyl groups or hydrogens along the way. Additionally, you can expect that this reaction will follow Markovnikov's rule in terms of where the H adds relative to the OH in the reaction. So with these two facts alone, we can go directly from the starting material to the product if you want, without drawing out a full mechanism to show how to do that. If all you're asked to do is provide the major product of this reaction, you can directly use Mark's rule to plug an H and an OH into the starting alkene to give the final product, the addition product. But we are going to go into the mechanism here because for many, the mechanism is helpful about remembering key facts about the reaction. If you know the logical basis for how it happens, that will allow you to predict what product to expect as the major product. So we're going to do that same example problem that we were looking at up top, where we started with this molecule, and we wanted to create an addition product that corresponds to adding H and OH across the carbon-carbon double bond, following Mark's rule, like so, but with no carbocation rearrangement. So the reagents that we will use to accomplish this is going to be first what we refer to as our oxymercuration reagent. Our oxymercuration reagent is going to be mercuric acetate, which I'll go ahead and abbreviate that for you. So it's mercury that is bonded to two O-acyl groups, and I will draw out the structure for that in just a moment, as well as in that reaction mixture, water. So this is going to comprise the oxymercuration component of the reaction. And notice how it's a hyphenated reaction, oxymercuration reduction. That means that we're going to do this in order. First, we'll run an oxymercuration reaction, so we put number 1 there to indicate that. And then after that reaction is totally finished, what we do then is do a reduction reaction. The reducing agent is typically going to be sodium borohydride, NaBH4. So this is a 2-step reaction, and the number 1 and number 2 there are critical, because what those indicate to us is that we have to add the first reagent first, wait for that reaction to finish, and then add the second reagent. You can't dump all those things in together, or they will cross-react, you won't get the right product, etc., etc. So number 1 and number 2 indicates the order in which those chemicals are added to the reaction mixture. We are going to go through the reaction mechanism for the first step of this reaction. So we're going to go through the oxymercuration mechanism here. The oxymercuration mechanism will dictate why it is the case that this reaction does not suffer from carbocation rearrangements. So this is going to be the most important part of the mechanism from the perspective of understanding why the reaction follows Mark's rule and why there's no carbocation rearrangement. So for the oxymercuration mechanism, what we will do is we'll start with our reactants, and we're going to be looking at our alkene. So I'm just redrawing the alkene starting material. And what will happen in this reaction mechanism, first off, is that when we take our oxymercuration reagent, our mercuric acetate, if we draw out the full structure of that, I abbreviated it up top as Hg for mercury bonded to two O-acyl groups. What we have is we have our mercury. Mercury is going to have one lone pair on it like so. It's directly bonded to an oxygen on one side, followed by a carbonyl group and a methyl group. And it's going to be bonded to the same thing over here. So this has some symmetry going on. So carbonyl group and our methyl group. And the way that we get that abbreviation of OAC2 is that we refer to this group as being an O-acyl group. So we put OAC there. So that's O for oxygen, and then our acyl group is what I will outline in blue here. It's our carbonyl group directly bonded to our methyl group. So that's what we abbreviate, highlighted in blue here, as AC in our reaction. And you'll see this abbreviation for a carbonyl group bonded to a methyl group in a variety of different contexts, not just here, but on down the road as well. So it's a good thing to keep in mind. So what's going to happen here is that mercury is our metal. So it is pretty deficient in electrons, and it is going to be attacked by the pi bond from our alkene. So the pi bond comes over, attacks the mercury atom, and that causes the oxygen carbon bond to break. So we end up, as our product of interest resulting from this reaction step, is we've done an addition of mercury across the carbon-carbon double bond. And we will follow Mark's rule here in deciding which of those two carbon atoms to put the mercury on. So the mercury is going to go to carbon number 1 of the chain, because that would allow us to do a carbocation at carbon number 2. So we'll go ahead and plug in our mercury here, and I'm going to do that in red. So we plug in our mercury, Hg. That mercury atom does have a lone pair of electrons right there because it had that to start with, so we haven't done anything to that, so that'll still be there. And then it's still going to have a bond to the O-acyl group, so oxygen and then carbonyl followed by a CH3. And we would expect there to be a formal charge of 0 on the mercury atom at this point in time. So we could describe in words this first step as our pi electrons there from the alkene attacking the mercury metal. The mercury metal is relatively electron deficient, and this will give us, following Mark's rule, so this is a Markovnikov type addition, that will give us our mercury organic compound intermediate that we see there. Additionally, that O acyl group up top, in the top right hand side of the equation right here, breaks away, and so I've also included that over here as an intermediate that we're generally not so concerned with. Usually we're concerned most with the organic intermediate and intermediates that are going to participate in future steps. So at this point now, we have that unique situation where we have an atom with a lone pair adjacent, on the carbon adjacent to a carbocation, much like the situation where we're adding Cl2 and Br2 across a carbon-carbon double bond, and we were able to put a chlorine or bromine here with a lone pair of electrons and do resonance to form a bridge over to the carbocation carbon. We can do the same thing here because we have that situation where we have a lone pair of electrons on the mercury atom, that mercury atom that's attached to the adjacent carbon from the carbocation. So we'll draw a second resonance structure here, and it's due to this resonance that we have no carbocation rearrangement take place, because resonance takes place of a carbocation rearrangement. Generally, if there's resonance to stabilize a molecule, carbocation rearrangements are not going to be a thing that occurs. So we'll go ahead and draw this in, and I'm going to color code my bonds here so that we showed the electron pushing arrows there in green, so I'm going to show the arrow in green. Our bond to mercury that was there to start with was in red, so I'm going to still show that in red. So we'll plug in our mercury here. That mercury is still bonded to our O acyl group. I'm going to fill in that O acyl group as an abbreviation because remember that OAC represents oxygen bonded to our carbonyl and methyl group, so we're good to go on that. And then keeping in mind our formal charges here, due to the fact that our mercury atom has taken a lone pair of electrons and that's now a covalent bond, that means we have less electrons that are under the jurisdiction of that mercury. The mercury is going to end up with a positive formal charge. So we're sharing that positive formal charge over the carbon atom and the mercury atom by forming this three-membered ring. As was the situation when we formed a three-membered bridge using chlorine or bromine, this second resonance structure with the three-membered ring is particularly stabilized by the fact that the number of covalent bonds is maximized here by doing this step. So we're good to go on that. And now what's going to happen is that we will have our nucleophile come in and attack one of these two carbon atoms that's bonded to the mercury. And just as a reminder, before we move on to that next step, I'm going to put a note here that there will be no carbocation rearrangement due to the fact that we have this three-membered resonance ring intermediate instead. So no carbocation rearrangement here because instead we have that resonance going on, and resonance more important generally than induction, and so if there's resonance to stabilize a molecule, no carbocation rearrangement is needed because that's not going to improve the stability of the intermediate. So let's go on to the next step. The next step of this process is going to be that the water that we had available in our net reaction there up at the top left corner in tiny print, that water is going to come in and act as a nucleophile attacking one of the two carbon atoms here or here. So let's go ahead and do that as step 2 of the mechanism. So we'll go ahead and redraw one of those two intermediates that I've circled in yellow there. I'm going to do the one that features our three-membered ring with our mercury bonded to OAC, positive formal charge on the mercury, and then we're going to bring in our water to act as the nucleophile, and I'm going to draw the full Lewis structure of our water here so we can show all the electrons there, keeping track of who's going where. And we'll go ahead and label this second step as the nucleophile attacks the more substituted carbon. And looking at these two carbon atoms here and here, the more substituted one is the one on the left. More substituted means has more alkyl groups directly bonded to it. So we want to do the attack at that carbon on the left, the one I just put the green dot on right now. And you can also recognize that as being the site that's more prone to attack, because that's going to be the site that is more electrophilic, meaning more positively polarized, because if we look up at those two resonance structures circled in yellow, one of those two structures has a positive formal charge on that carbon that I've put the green dot on down here, and so that means that's going to be the more electrophilic of the two carbon atoms. So it's going to be the one that's most poised to be attacked by the nucleophilic oxygen. So nucleophilic oxygen comes over, forms a covalent bond to that carbon. That forces the carbon-mercury bond to break, with the electrons going on to our mercury atom. So this step where the nucleophile attacks the more substituted carbon is completely analogous to the situation where we had reactions with an alkene plus Cl2, where the first Cl would come in, form a three-membered bridged intermediate, and then the second Cl would come in and attack at the more substituted carbon, forcing that three-membered ring to break open. Same situation here, and it's the same reason here as in the chlorination reaction that we did not have carbocation rearrangements taking place, because the bridge takes priority in determining the stability of the molecule. So go ahead and draw out our intermediate here. So we'll have a positive charge on the oxygen now of that water that just come in and formed a bond. And then we have our mercury coming in right here. And I'm going to abbreviate OAC again. And our mercury, being careful here to keep track of our electrons. Our mercury originally had 3 bonds to it. And now that we've broken one of those bonds, that bond has become a lone pair of electrons. So that was the bond right here, broke. Those electrons went onto the mercury to become that lone pair right here. So now we have on the mercury a lone pair of electrons and 2 covalent bonds. Those 2 covalent bonds are the bonds that go to the OAC, which is shown over here, and the bond to the carbon right there. So now then, we have our intermediate that has the mercury as well as the water directly bonded to it. And so that's going to show where the hydroxy group is going to end up in the final product, because the hydroxy group is going to end up right here by deprotonating that water. Now then, at step 3, we'll show that deprotonation step. So step number 3, we're going to remove a proton from water. And we can illustrate that happening by bringing in another unit of water to act as our base, much like what we did with our earlier hydration reactions. So water comes in, acts as a base to grab that proton, forcing the oxygen-hydrogen bond to break, and leaving us with what we refer to as our organomercurial alcohol. So we'll go ahead and draw out our organomercurial alcohol. Now we have our hydroxy group right there. And you'll notice that this corresponds to having used Mark's rule to add a hydroxy group across the carbon-carbon double bond. And we still have in our situation right now our mercury OAC right there. So this is as far as we're going to go with this particular reaction mechanism. We're going to stop here with showing the so-called organomercurial alcohol. And what would happen following this is that the organomercurial alcohol would then be subject to the reduction reaction. So you'll notice if we look up here in the upper left corner that I've just enlarged now, we started off with step 1 of the reaction being reacting with mercury and water. And we showed the mechanism for all of that just now. Then the second thing that happens is the reduction reaction with sodium borohydride. We are not going to go through the mechanism for that. I don't expect you to know that mechanism, but I am going to fill in here that our reduction reaction, I'm just going to put reduce with sodium borohydride, NaBH4, and what that's going to do is result in the breakage of the bond between carbon and mercury right there, and replacement of that bond with a hydrogen from our hydride reagent, from our sodium borohydride. So our final product here, then, that we would observe in our reaction mixture after we do both steps 1 and 2, oxymercuration followed by reduction of our molecule, is going to be that CH2 group right here becomes a CH3 group by replacing the mercury there with a hydrogen. So this is going to give you your final product. You'll notice that we do have a chiral center in the final product. That chiral center would end up being a mixture of the R and S enantiomers for this acyclic situation. So we'd have dash for one, wedge for the other to make both of the two enantiomers. So in this case, this particular situation would not be stereoselective because we're making both of the two possible stereoisomer products. We would, however, say that the reaction is regioselective because we're following Mark's rule. And additionally, we're introducing that extra layer of regioselectivity where we're not even doing a carbocation rearrangement here. So definitely very regioselective in this particular example problem. So what if we had a situation where we were working with a cyclic alkene starting material? Are there constraints on the stereochemistry of the product that could make the reaction stereoselective? So we're going to take a look at that situation now for a cyclic alkene and see how that impacts things. So straight away, I'm going to give you a spoiler alert, and that is that cyclic alkenes are going to give anti-addition of water using oxymercuration reduction. So you'll remember that when we were doing addition of water to alkenes using acid catalysis, we would see that the reaction was not stereoselective, that you would get a mixture of all the different possible stereoisomers using water and acid. But now if we use oxymercuration reduction instead, we get a stereoselectivity preference for anti-addition. So we would describe this situation as being stereoselective because we prefer to make the anti-configuration. So why do we prefer to make the anti-configuration? Let's illustrate that for an example problem. And in order for this example problem to work out, we need to make sure that we are going to have some chiral centers in our final product. So what I'm going to do is I'm going to start with a starting material here that has two methyl groups. So this would be 1,2-dimethyl, 1-cyclohexene. We're going to react it with our oxymercuration reduction mixture. So what you'll always be looking for here is training yourself to look for an alkene that's reacting first with mercury and water. So we're reacting with our mercuric acetate, HgOAC2, and water, followed by reduction with sodium borohydride. So now that we've got our sodium borohydride in there to finish off the reaction, let's look at the mechanism for the oxymercuration step to understand why this reaction is going to have a stereoselective preference for giving anti-addition when we have this ring structure to start with. So we go ahead and do the beginning stages of the mechanism the same as we did our example up top here. So I'm starting off with our mercuric acetate, abbreviating, remember that acetate unit there is OAC. And we'll start remembering that there's a lone pair of electrons on the mercury there. The mercury, however, is a metal, so it's rather electron deficient. The pi electrons are going to be drawn to it. So they form a bond to there. Oxygen has to break away. And what's then going to happen is that we get our carbocation intermediate that will be stabilized by resonance. So we've added Hg, mercury, to one of those two carbons. It doesn't matter which of the two you add it to, since in this particular situation we have symmetrically substituted carbon atoms. So we'll go ahead and do this here. That will result in the placement of our carbocation right here. And we would also have our OAC anion resulting there, but we don't really care so much about that. So I'm just going to write it off to the side. And then what's going to happen is that we'll have that resonance stabilization. We don't think of this as a separate step of the mechanism. Instead, it's just something that's automatically going to be in place. As soon as this reaction occurs, the actual structure of the intermediate is going to be an average of the two resonance structures that I'll draw. So mercury comes over, forms a covalent bond to that carbocation to make our three-membered bridge structure. So I'll go ahead and draw our three-membered bridge structure here. And that 3-membered ring is connected directly to our 6-membered ring. So we have our 2 methyl groups, and then our bonds leading to the mercury. And that mercury is bonded to our OAC. And keep in mind that when we're looking at this, those 2 bonds to mercury have to be in the same face of the molecule. So they both have to be wedges or both have to be dashes. Otherwise, one of the bonds would need to be so long that it would not be able to exist. So we draw 2 wedges there. Or alternatively, the other stereochemistry that will also be present is that those would be 2 dashes instead. So we could draw dash, dash to the mercury, OAC instead. And keep in mind that these methyl groups then we could put as wedges there and dashes here to fill in the complete tetrahedron. I also need to keep in mind my formal charges. So I'm going to fill in formal charge +1 on the mercury here and here. Now the importance of this is that remember those 3-membered ring structures are major resonance contributors. And so they're going to have a major impact on what the stereochemical outcome of this reaction is. And at the next step, that's when the nucleophile attacks the water. And that means that the water will have to attack from the side opposite where the mercury is. So the water nucleophile comes in, it attacks one of those 2 carbon atoms right here, forcing the carbon-mercury bond to break like so. And the attack of that water on our carbon atom up here has to be from the back. And the reason it has to be from the back is that that mercury-carbon bond is breaking from the front side of the molecule because that's shown as a wedge. So when that mercury-carbon bond breaks on the front side of the molecule, that's creating too much steric hindrance for the water to come in and attack from the front at the same time that that breakage is occurring. So there has to be an attack from the back. This is much like the situation of the SN2 reaction where we had the backside attack occurring to minimize the steric hindrance. Same thing here. So the water comes in, attacks the carbon right here as you could think of that carbon-mercury bond with the mercury as being the leaving group. So that carbon-mercury bond is breaking at the same time the nucleophile is attacking, and that's going to force the attack to occur of the water on the carbon from the front side in this bottom situation because the mercury atom is on the back side. So we have to minimize steric hindrance. So the outcome of this is that if we're looking at the stereochemistry here, due to the fact that that 6-membered ring locks the atoms into place, we can't freely rotate around the carbon-carbon bond here to reorient the molecule during this process. That bond shown in yellow is stuck in place. We have to have attack from the back and front respectively, and that will result in the water and mercury being trans to one another. So the water and mercury end up trans to one another, therefore we would describe this as an anti-addition of our mercury and our water. So going ahead and drawing this in to show our intermediates here. Our water attacks from the back in the top scenario, so therefore the water is going to be oriented toward the back. That means that that methyl group would have to be coming to the front now. And then down here, our mercury started off as a wedge. Nothing happened to that carbon-mercury bond that's shown in red there. So it's still there, HGOAC, and the methyl group that's there is still oriented to the back. So this is what I've drawn here on the lower part of this screen would correspond to that first intermediate and the mechanism going on there. Now, I'll go ahead and show you the other intermediate here that is also going to correspond to anti-addition. So that's going to have the attack of water from the front, so we'll show the water on a wedge, OH2, and we need our positive formal charge on there, as we did over here, but I kind of left out. And we need our dash to the methyl group, since the water is going to push that methyl group out of the way. And then coming down below, our mercury atom is going to be shown on a dash. So we do dash to mercury, OAC. And you'll notice here that in both of these cases, the mercury and the water are trans to one another. Water is a wedge here, mercury is a dash, or vice versa. So this is going to give stereoselectivity because these two groups are not going to end up cis to one another. Instead, they're going to end up trans to one another. So we describe this definitely as anti-addition of our mercury and our water. And this pattern of these groups being anti to one another will continue all the way through the reaction, through the deprotonation step and through the reduction of that mercury to a hydrogen atom, giving us a final product that will be corresponding to the H and the OH in the final molecule being trans to one another. So anti continues onward here toward the final product. So we do deprotonation, which I'm not going to show, just removing that proton from the OH2, and then the reduction reaction, reduce with NaBH4, and we did not go through the mechanism for that. You're not expected to know that mechanism. It's beyond the scope of the class, but that reduction reaction is not going to change the stereochemistry here. It's just going to result in replacement of the mercury atom with a hydrogen atom. So we're going to end up with, based on the intermediate on the left there, we'll end up with our H going right here on a wedge, methyl coming down. Based on the structure on the right, on the other hand, we'll have our OH group on a wedge up top, methyl group on a dash, and down below we'll have our H on a dash and our methyl group on a wedge to give these two stereoisomer product. And this is a situation where we would describe this as being stereoselective. It's stereoselective for making the anti-product, anti corresponding to the OH and H going in opposite orientations as the preference here and here. And since we have two chiral centers here, in theory we could make 4 different stereoisomer products. In actuality, we only make 2, so this is definitely stereoselective in this oxymercuration reduction reaction. And the bottom line here with oxymercuration reduction in general is that it's going to be a valuable way to do addition of water across a carbon-carbon double bond following Markovnikov's rule without carbocation rearrangements being a worry. And in the case of these cyclic systems, you can get a stereoselective trans addition occurring. So keep those facts in mind with regard to this reaction.